Bismillahirrahmanirrahim. Today we are going to discuss a new technology, that is the carbon dioxide sequestrating with reference to the environmental chemistry. Carbon dioxide sequestering. Carbon sequestration or carbon dioxide removal is abbreviated as CDR, is the long-term removal, capture or sequestration of carbon dioxide from the atmosphere to slow or reverse atmospheric carbon dioxide pollution and to mitigate or reverse global warming. Carbon dioxide is naturally captured from the atmosphere through biological, chemical, and physical processes. These changes can be accelerated through changes in land use and agricultural practices, such as converting crop and livestock grazing land into the land for non-crop fast-growing plants. Artificial processes have been devised to produce similar effects, including large-scale artificial capture and sequestration of industrially produced carbon dioxide using surface or subsurface saline aquifer reservoirs, ocean water, aging oil fields, or other carbon sinks. Biological energy with carbon capture and storage, biochar, ocean fertilization, enhanced weathering, and direct air capture when combined with storage. Carbon sequestration is the process involved in carbon capture and the long-term storage of atmospheric carbon dioxide and may refer specifically to: number 1, the process of removing carbon from the atmosphere and depositing in a reservoir. When carried out deliberately, this may also be referred to as carbon dioxide removal, which is a form of geoengineering. Number 2, carbon capture and storage, where carbon dioxide is removed from the flue gases before being stored in the underground reservoirs. Number 3, natural biogeochemical cycling of carbon between the atmosphere and reservoirs, such as by chemical weathering of rock. Carbon dioxide may be captured as a pure byproduct in processes related to petroleum refining or from the flue gases from power generation. Carbon dioxide sequestration includes the storage part of carbon capture and storage, which refers to large-scale artificial capture and sequestration of naturally and industrially produced carbon dioxide using subsurface saline aquifer reservoir, ocean water, aging oil field, or other carbon sinks. Carbon sequestration describes long-term storage of carbon dioxide or other forms of carbon to either mitigate or defer global warming and avoid dangerous climate change. It has been proposed as a way to slow the atmospheric and marine accumulation of greenhouse gases which are released by burning fossil fuels. Carbon dioxide is naturally captured from the atmosphere through biological, chemical, or physical processes. Some artificial sequestration techniques exploit these natural processes while some use entirely artificial processes. There are three ways that is sequestration can be carried out. Number one, post-combustion capture. Number two, pre-combustion capture. Number three, oxycombustion. A wide variety of separation techniques are being pursued, including gas phase separation, absorption into a liquid, and adsorption on a solid, as well as hybrid processes such as adsorption coming with membrane system. These are above processes basically capture carbon dioxide or carbon emitting from power plants, factories, fuel burning industries, and so on, which is used by organizations as they look to reduce carbon emissions from their operations. In post-combustion capture, the carbon dioxide is removed after combustion of the fossil fuel. This is the scheme that would be applied to fossil fuel burning power plants. Here, carbon dioxide is captured from flue gases at power stations and other large point sources. The technology is well understood and is currently used in other industrial applications, although not at the same scale as might be required in a commercial scale power station. Post-combustion capture is most popular in research because existing fossil fuel power plants can be retrofitted and include to CCS technology in this configuration. The technology for pre-combustion is widely applied in fertilizer, chemicals, gaseous fuels such as hydrogen and methane, and power production. In these cases, the fossil fuel is partially oxidized, for instance, in a gasifier. The carbon monoxide from the resulting syngas, that is carbon monoxide and hydrogen, results with added steam and is shifted into carbon dioxide and hydrogen. The resulting carbon dioxide can be captured from a relatively pure exhaust stream. The hydrogen can now be used as fuel. The carbon dioxide is removed before combustion takes place. These are several advantages and disadvantages which, when compared to conventional post-combustion carbon dioxide capture. The carbon dioxide is removed after combustion from fossil fuels, but before the flue gases is expanded to atmospheric pressures. This scheme is applied to new fossil fuel burning power plants or to existing plants where repowering is an option. The capture before expansion, that is from pressurized gas, is standard in almost all industrial carbon dioxide capture processes at the same scale as required for power plants. Oxyfuel combustion. Oxyfuel combustion, the fuel is burned in oxygen instead of air because air is a mixture of different gases. To limit the resulting flame temperature to level common during the conventional combustion, cooled the flue gases is recirculated and injected into the combustion chambers. The flue gas consists of mainly carbon dioxide and water vapor, the latter of which is condensed through cooling. The result is an almost pure carbon dioxide stream that can be transported to the sequestration site and stored. Power plant processes based on oxyfuel combustion are sometimes referred to as zero emission cycle because the carbon dioxide stored is not a fraction removed from the flue gas streams, as in the case of pre and post combustion capture, but the flue gas streams itself. A certain fraction of the carbon dioxide generated during combustion will inevitably end up in the condensed water. To warrant the label zero emission, the water would thus have to be treated or disposed of appropriately. Biological processes. Biosequestration or carbon sequestration through biological process affects the global carbon cycle. For example, include major climate fluctuations such as the Azola event, which created the current Arctic climate. Such processes created fossil fuels as well as laterite and limestone. By manipulating such processes, geoengineers seek to enhance sequestration. Biological processes include number 1, peatlands. Peat bogs act as a sink for carbon due to the accumulation of partially decayed biomass that would otherwise continue to decay completely. There is a variance on how much the peatlands act as a carbon sink or carbon source that can be linked to varying climates in different areas of the world and different times of the year. By creating new bogs or enhancing existing ones, the amount of carbon that is sequestrated by bogs would increase. The second is the wetland restoration. Wetland soil is an important carbon sink, that is about 14.5% of the world's soil. Carbon is found in wetland, while only 6% of the world's land is composed of wetland. Reforestation is the replanting of trees on marginal crops and pasture lands to incorporate carbon from atmospheric carbon dioxide into the biomass. For this carbon sequestration process to succeed, the carbon must not return to the atmosphere from the mass burning or rotting when the trees die. To this end, land allotted to the trees must not be converted to other uses, and management of the frequency of distribution or disturbance might be necessary in order to avoid extreme events. Alternatively, the wood from them must itself be sequestrated, for example, via biogas, energy with carbon stored, landfill or stored by use in, for example, construction, short of growth in perpetuity. However, reforestation with long-lived trees that is more than 100 years will sequester carbon for substantial period and be released gradually, minimizing carbon's climate impact during the 25th century. Earth offers enough room to plant an additional 1.2 trillion trees. Planting and protecting them would offset some 10 years of carbon dioxide emission and sequester 205 or 205 billion tons of carbon. This approach is supported by the Trillion Tree Campaign. Restoring all degraded forests world would capture about 205 billion tons of carbon in total, which is about two-thirds of all carbon emissions. Still, mangroves are one of the best way to store carbon. Mangrove ecosystems are long-term carbon sinks that remove carbon dioxide from the atmosphere and store it in their biomasses for thousands of years. The next is urban forestry. Urban forestry increases the amount of carbon taken up in cities by adding new tree sites, and the sequestration of carbon source occurs over the lifetime of the tree. It is generally practiced and maintained on small circles like in cities. The result of urban forestry can have different results depending on the type of vegetation that is being used, so it can function as a sink but can also function as a source of emission. Along with sequestration by the plant, which is difficult to measure but seems to have little effect on the overall amount of carbon dioxide that is uptaken. The vegetation can have indirect effect on carbon by reducing need for energy consumption. Carbon farming. Carbon farming is a name for a variety of agricultural methods aimed at sequestrating atmospheric carbon into the soil and in crop roots, wood and leaves. Increasing soil carbon content can aid plant growth, increase soil organic matter, improve soil water retention capacity, and reduce the fertilizer use. As of 2016, the variant of carbon farming reached hundreds of millions of hectares globally. Of the nearly 5 billion hectares of world farmland, soils can contain up to 5% carbon by weight, including decomposing plants and animal matter and biocars. Potentially, sequestration alternatives to carbon farming, including scrubbing carbon dioxide from the air with the machines, fertilizing the ocean to prompt algal blooms that after death carry carbon to the sea bottom, storing carbon dioxide emitted by electricity generation, and crushing and spreading types of rock such as basalt that absorb atmospheric carbon. Land management techniques that can be combined with farming include planting or restoring forests, burning biochar produced by the anaerobically converted biomass, and restoring wetlands. Agriculture. Compared to natural vegetation, cropland soils are depleted in soil organic carbon. When a soil is converted from natural land or semi-natural land such as forests, woodlands, grasslands, steppes, and savannas, the soil organic carbon content in the soil reduces by about 30 to 40%. This loss is due to the removal of plant material containing carbon. In terms of harvest, when the land use changes, the carbon in the soil will either increase or decrease. This change will continue until the soil reaches a new equilibrium. Deviation from this new equilibrium can also be affected by variated climate. The decreasing of soil organic carbon content can be counteracted by increasing the carbon input. This can be done with several strategies. For example, leaf harvest residues on the field, use manure as a fertilizer, or include perennial crops in the rotation. Perennial crops have large below ground biomass fraction which increases the soil organic content, carbon content. Globally, soils are estimated to contain greater than 8,580 gigatons of organic carbon, about 10 times the amount in the atmosphere and much more than in vegetation. Modification of the agricultural practice is a recognized method of carbon dioxide or carbon sequestration, as the soil can act as an effective carbon sink, offsetting as much as 20% of 2010 carbon dioxide emission annually. Carbon emission reduction method in agriculture can be grouped into two categories. Number one is the reducing and number two is the displacing emission groups or enhancing carbon removal. Some of these reductions involve increasing the efficiency of farm operations, while some involve interruption in the natural carbon cycle. Also, some effective techniques can negatively impact other environmental concerns. Bamboo farming. Although a bamboo forest stores less total carbon than a mature forest of trees, a bamboo plantation sequesters carbon at a much faster rate than a mature forest or a tree plantation. Therefore, the farming of bamboo timber may have significant carbon sequestration potential. Next method is the deep soil. Soil holds 4 times the amount of carbon stored in the atmosphere. About half of this is found deep within soil. About 90% of this deep soil carbon is stabilized by mineral organic association. Now, the reducing emission. Increasing yields and efficiency generally reduces emission as well as since more food results from the same or less effort. Techniques include more accurate use of fertilizers, less soil disturbance, better irrigation and crop strains, breed for local beneficial traits and increasing yields. Replacing more energy intensive farming operations can also reduce emissions. Reduced or non-till farming requires less machine use and burns correspondingly less fuel per acre. However, non-till usually increases use of weed control chemicals and the residue now left on the soil surface is more likely to release its carbon dioxide to the atmosphere as it decays. In practice, most farming operations that incorporate post-harvest crop residue, waste, and byproducts back into the soil provide a carbon storage benefit. This is the particular case for practices such as a fuel burning of stubble rather than releasing amount all of the stored carbon dioxide to the atmosphere. Tillage incorporates the biomass back into the soil. Enhanced carbon removal. All crops absorb carbon dioxide during growth and release it after harvest. The goal of agriculture carbon removal is to use the crop and its relation to the carbon cycle to permanently sequester carbon within the soil. This is done by selecting farming methods that return biomass to the soil and enhance the conditions in which the carbon within the plant will be reduced to its elemental nature and stored in the stable state. Methods for accomplishing this include number 1. Use cover crops such as grasses and weeds as temporarily covered between planting seasons. Number 2. Concentrate livestock in small paddock for days at a time so that they graze slightly but evenly. This encourages roots to grow deeper into the soil. Stock also till the soil with their hooves, driving old grass and manures into the soil. Number 3. Cover bare paddocks with hay or dead vegetation. This protects soil from the sun and allows the soil to hold more water and be more attractive to carbon capture microbes. This last one is the restore degraded lands, which slows carbon release while returning the land to agriculture or other use. Agriculture sequestration practices may have positive effect on soil, air and water quality, be beneficial to wildlife and expand food production. On degraded cropland, an increase of 1 ton of soil carbon pool may increase crop yield by 20 to 40 kilograms per hectare of wheat, 10 to 20 kilograms per hectare of maize, and 0 to 1 kilogram or 0.5 to 1 kilogram per hectare for cowpeas. This effect of soil sequestration can be reversed if the soil is disturbed or tillage practices are abandoned. The soil becomes a net source of greenhouse gases typically after 15 to 30 years of sequestration. Soil becomes saturated and cease to absorb carbon. This implies that there is a global limit to the amount of carbon that soil can hold. Many factors affecting the cost of carbon sequestration, including soil quality, transaction cost, and various externalities such as leakage, unforeseen environmental damage, because reduction of atmospheric carbon dioxide is a long-term concern. Farmers can be reluctant to adopt more expensive agricultural techniques because there is not a clear crop, soil, or economic benefit. Governments such as Australia and New Zealand are considering allowing farmers to sell carbon credit once they documented that they have sufficiently increased soil carbon content. Thank you.